I hope that we are ready to go to our next presentation, which is devoted to interpretable natural language segmentation based on linked grammar. And authors of these presentations are Vignar Ramech and Anton Kolonin. Welcome.
Hi, yes, I can share my screen. Can you see this?
Yes, I see your screen.
Okay,
I see your
great,
slides.
awesome. Okay, hello everyone. My name is Vignar Ramesh. The topic of my research with Dr. Anton Kolonin is interpretable natural language segmentation based on link grammar. So as a quick overview, I'll first start with an introduction on what natural language segmentation is and possible sources of unsegmented text that can be fed into our pipeline, and then the motivations of our work and what link grammar is as well. Then I will discuss our methodology and results and conclude with applications and future work. So natural language segmentation is the process of dividing written text into meaningful units, such as words, sentences, topics, or paragraphs. Text segmentation encompasses a variety of problems, such as word segmentation or intent segmentation, and our work is concerned with sentence segmentation. So sentence segmentation is the problem of dividing a string of natural language text into its component sentences. And note that we refer to sentence segmentation specifically in the context of separating bodies of text into valid sentences solely based on the grammatical relationships between individual words, meaning that we do not take into account punctuation, capitalization, or other syntactic structures that may be specific to certain languages. This allows our approach to generalize to various languages other than English, since not all written languages contain punctuation characters useful for approximating sentence boundaries. There are two primary sources of unsegmented text on which our proposed NLS algorithm can operate. First is the text output from speech-to-text, or STT, recognition engines, which are often used to pre-process the inputs of voice-activated question answering or chatbot pipelines, and the second is crawled web pages. STT engines transcribe audio content and return sequences of tokens without delimiters. Similarly, web scraping returns raw HTML and CSS output. The returned content often does not contain proper punctuation, and HTML or CSS tags are usually neither accurate nor consistent sentence boundary identifiers. In both these scenarios, our NLS architecture can be used to perform sentence segmentation without requiring the presence of delimiters. So, our first motivation is interpretable natural language processing. And to understand what INLP is, we must first understand the concept of explainable AI, or XAI. So XAI refers to AI methods whereby both the AI model and its results can be reasonably understood by humans. It contrasts with the idea of black box algorithms, where the AI model and its outcome cannot be understood even by the developer. INLP is an application of the XAI concept to natural language processing. It allows for the learning of natural language material, comprehension of bodies of text, and generation of textual material via logical and transparent methods that rely on interpretable models of formal grammar, such as link grammar, which I'll discuss soon. The other main benefit of INLP models is that they mitigate blind spots in corpora and allow model errors to be located. What this means is, in a black box algorithm, the developer may not know whether poor performance is due to a model error or an inconsistency in the testing corpus or a training corpus for supervised models, and so on. INLP solves this issue because these methods can be easily understood by humans and errors can be easily located. The main takeaway from this motivation is that our NLS method is expected to serve as an INLP algorithm, allowing for interpretable segmentation of large bodies of text into valid sentences. And we do so by providing explainable results and utilizing link grammar, which is an explainable formal grammar. On this slide, we see a diagram of the question answering pipeline, which is our second motivation. Question answering is the problem of automatically answering questions posed by humans in the form of natural language material via computational means. Within an explainable question answering pipeline, there exist two primary components: natural language comprehension and natural language generation. NLC requires first parsing the question, or input query, using a knowledge base structured as a formal grammar, and then performing semantic interpretation, which is learning semantic relationships between tokens of the parsed query found in the previous step. Our work focuses on voice-activated question answering pipelines, where the input query is captured as an audio recording and transcribed via an STT engine. The NLG component then involves semantic query execution, which is deriving the answer to the query using the relationships extracted during NLC, and then sentence construction, which involves building grammatically valid sentences from the words and relationships determined during query execution. Our work is concerned with both parsing the question as well as semantic query execution. While parsing the input query, our NLS architecture can first separate the token sequence that represents the question into its component sentences, which can then be passed on to the semantic interpretation step. Semantic query execution matches relevant text with the input query, often expressed as a set of keywords between which exist various semantic relationships. Given an NLP architecture that deals with the problem of matching the query with available documents, such as those available on the internet, we focus on segmenting these documents into their grammatically valid component sentences. A subset of these sentences most relevant to the input query can then be passed on to the relationship extraction and sentence construction steps of the NLG component of the question answering pipeline. Now on to linked grammar. Linked grammar is based upon the idea that every word possesses a feature structure that contains a set of typed connectors. A sentence refers to a set of tokens, so words, punctuation, or other syntactic structures, that can be connected by matching up connectors between certain pairs of tokens. And here are a few statistics about the linked grammar database structure. Here we see a few diagrams of linked grammar. The first picture shows an excerpt of the linked grammar database, which maps all common words of a given language to the connectors that define them. The second image is a visual representation of the set of connectors corresponding to a few words, as specified in the linked grammar dictionary. Disjuncts are sets of connectors that define the valid use of a given word. For instance, in this given example, the words cat and snake both have two disjuncts, D minus, S plus, and D minus, O minus. Okay, the third image shows how connectors can link these words together to form the sentence, the cat chased a snake. And finally, on the last image, we see the same sentence in graphical form. This is to help us visualize the additional constraints beyond the matching of connectors that linked grammar requires, namely the planarity and connectivity meta rules. Planarity means that links cannot cross, and connectivity means that the links and tokens of a sentence must all form a connected graph wherein all tokens are connected to each other via some path. Before we can continue, we must answer one important question, which is why did we choose linked grammar? Besides linked grammar, other grammar rule dictionaries and APIs exist, such as S.A.I.ence and universal dependencies. Solutions such as S.A.I.ence are programming language-specific APIs or packages. For instance, S.A.I.ence restricts its grammar database to applications developed in Python. Moreover, S.A.I.ence relies on a dependency grammar, which requires a head-dependent relationship, meaning that links must be directional. Linked grammars does not require links to indicate direction, and thus can be applied to a greater variety of sentential forms. Universal dependencies, or UD, and similar alternatives require knowledge of each word's part of speech, which leads to very complex connector expressions and rule formats. Linked grammar not only provides flexibility across multiple programming languages, but also is relatively simple. Unlike grammar databases such as UD that include specific rules based on parts of speech, linked grammar solely focuses on links between words and has interpretable meta rules. Now I will discuss the methodology of our approach. So here is a diagram of our proposed NLS architecture. As you can see, there are two main components, the loader and segment. Loader produces a dictionary object from a linked grammar dictionary file. This dictionary can then be used in a parser, which creates parsers of sentences that can be used to process the input query during the first step of the question answering pipeline shown in the right of the image. The dictionary also feeds into the segment, which is the core of our work, and I will discuss this soon. So loader loads and stores the linked grammar database in various classes for future usage. Specifically, as shown in the diagram below, the dictionary class stores a list of word objects. Each word object contains a unique rule object. A rule contains a list of disjunct objects, and each disjunct stores a list of connectors that constitute the legal use of the given word. Currently, the loader architecture only supports the English language and does not handle more complex morphological structures, including those needed to support languages such as Russian that require extensive morphology usage. As shown in the algorithm to the right, the makeDict function, which comprises the core of the loader, utilizes the information in an array of lines obtained from the linked grammar database to create an array of dictionary objects that map each common word or phrase that linked grammar supports to its associated rule. To do so, it extracts a linked grammar rule from each element of the array lines, storing any new macros, which are single links that define larger connector expressions, in the data structure macros. The algorithm then replaces each macro within the current rule with its expanded expression and assigns the modified rule to the word it defines. This mapping between words and their connector expressions forms the dictionary objects that are then sent to the segment class. Given the dictionaries generated by the loader, the segment class computes a segmentation for a string of text by first extracting the tokens, which are words and punctuation, from that text via the process sentences function, and then clustering those tokens into valid sentences as per the segment function. As shown in the image to the right, the segment function loops through the input array, tokens, and determines if certain subsets of those tokens can form grammatically valid sentences using the isValid and check functions. IsValid determines if the array, R, which is the input, can form a grammatically valid sentence via linked grammar rules, by ensuring that every pair of consecutive tokens in R can be connected via links given in the dictionary objects created by the loader. To do so, isValid uses the connects function, which returns a Boolean value indicating whether its two parameters, the tokens left and right, can be linked together. As shown to the right, connects determines the lists of rules left list and right list that corresponds with the tokens left and right, and then checks if any disjunct in any rule in left list matches with any disjunct in any rule in right list. The check function simply determines if the first two tokens following R satisfy initial checks of the planarity and connectivity meta rules, and this also serves to decrease the runtime. For example, one partial connectivity check that check implements involves ensuring that the first and second tokens after R are capable of forming links to the right and left, respectively. Below, you see an example segmentation query. So passing in the continuous stream of text, tuna is a fish, eagle is a bird, dog is a mammal, yields the three sentences, tuna is a fish, eagle is a bird, and dog is a mammal. Our algorithm was tested on two distinct corpora. When tested on 88 sentences with words all part of SingularityNet's Small World POC English corpus, which contains 88 total sentences with an average of 5 to 6 tokens per sentence, our algorithm segmented the corpus text into 87 total sentences and achieved an accuracy of boundary identification of 97.7%. When tested on an excerpt of Lucy Maud Montgomery's Anne's House of Dreams, as found in the Gutenberg Children corpus, our algorithm accurately identified 7 of 9 sentence boundaries and segmented the text into 11 total sentences, 1 sentence more than the ground truth. We compared our NLS architecture to 3 widely used open source sentence segmentation frameworks: Syntalk, PragmaticNet, and DeepSegment. Syntalk computes segmentations by recognizing terminal markers, which are syntactic structures such as periods, exclamation marks, question marks, and so on, that signify sentence boundaries. PragmaticNet is an unsupervised, opinionated, and conservative segmentation framework that, similar to Syntalk, segments text into sentences based on punctuation, quotation, and parentheticals. Both Syntalk and PragmaticNet identified 0 boundaries in the text from both the POC English corpus and the Gutenberg corpus, thereby returning 1 total sentence for each corpus and yielding an accuracy of 0%. Since Syntalk and PragmaticNet rely on punctuation and other syntactic structures for segmentation, they are unable to segment bodies of text without punctuation. Next, DeepSegment utilizes bidirectional long short-term memory networks, or bi-LSTMs, in a CRF, or conditional random field, based supervised segmentation model aimed at segmenting unpunctuated bodies of text into sentences. Even though it does not rely on punctuation, DeepSegment still identified only 1 segmentation boundary in the POC English corpus and 2 boundaries in the Gutenberg corpus, all of which were accurate, yielding accuracies of 1.15 and 22.2% respectively. Our proposed NLS architecture far exceeds these open source baselines and, most importantly, provides accurate support for unpunctuated bodies of text, thus generalizing to segmentation tasks across languages with varying syntactic structures. We found that the accuracy of our results was affected primarily by the issue of grammatical ambiguity, which refers to situations in which the same word may take on different parts of speech. Consider the string of text, dad has a hammer, mom has a hammer. It would be grammatically appropriate to segment this text into the 2 sentences, dad has a hammer and mom has a hammer, because the words hammer and mom cannot be connected via linked grammar rules. However, this is only true for the noun form of hammer. The verb form of hammer can technically be linked to the object mom. The presence of these grammatically correct, yet contextually wrong phrases decreased our sentence boundary identification accuracy. Semantic or word sense disambiguation, a solution to the grammatical ambiguity problem, determines which sense or definition of a word is activated by that word's use in a particular context. For instance, the word saw, when used in the sentence, the child saw a dog, will have a different sense and thus different link grammar rules than when used in the sentence, the carpenter is holding a saw. Current unsupervised semantic disambiguation methods include dictionary-based algorithms that utilize knowledge encoded in lexical resources to learn the senses of words. Implementing one such method will be part of our future work. So our NLS architecture can primarily be applied to the semantic query execution component of the question answering pipeline. One such scenario is the A.I.ence social media intelligence platform. Currently, the A.I.ence framework only handles written text in the form of oversimplified Pidgin English. Our NLS algorithm can enable agents to support question answering from spoken audio input transcribed by STT, as well as extract information from crawled web pages to answer such questions. Next is text simplification, which is the process of enhancing a corpus of human-readable text as to simplify the grammar and structure of the text while maintaining the original meaning. For instance, consider the unclear sentence, "Mom saw dad, who saw mom sawing." This text would be much simpler if split into the following three sentences: Mom saw dad saw mom, and mom was sawing. Our segmentation algorithm can be extended to perform text simplification, thereby improving the quality of corpora that would otherwise contain vocabulary and complex sentence constructions not easily processed via computational means. And more generally, our architecture can be applied to any NLP algorithms that operate at the sentential level, including automatic summarization, entity extraction, which is identifying and classifying important elements of a text into predefined categories, and sentiment identification, which is extracting emotions and opinions presented in a text. Our further work will be dedicated to, first, implementing semantic disambiguation, and second, extending our algorithm segmentation capabilities to languages other than English, including those that require heavy morphology usage. Our code and data set are publicly available on GitHub, and please feel free to contact me via email with any additional questions, and thank you for your attention.
Thank you for your speech, for your interesting speech. Colleagues, do you have any questions for speaker? Okay, so I have several questions.
I have one question.
Okay, Evgeny.
Why such small data sets were taken for evaluation?
Yeah, so we chose the POC English corpus to do our first evaluation because it had a very specific subset of link grammar rules that were not present in the overall link grammar database. So we decided to use this first to make sure it could extend to a variety of words. And then we tested the Gutenberg corpus in order to test additional words that were part of everyday storybooks and those kinds of sources. But as part of our further work, we definitely want to evaluate our model on larger corpora, such as the Brown and Reuters corpus.
Okay, thank you. You told that your approach is good for output, for plain text from output of speech to text systems,
Yes.
recognition systems, for example. But why do you not apply your algorithm to such data sets as DSTC, direct state tracking competitions? These competitions, as I know, these competitions are devoted to dialect systems on special texts from speech recognition systems. For example, there are no uppercases, there are no commas, etc. in these texts, and these corpora are standard for dialect system testing. And I think that it will be very interesting estimate your approach on such datasets.
Yes, I definitely agree. I think for now we started out with the POC English and Gutenberg corpus to initially test our results, but we'll definitely in the future be looking into corpora that are focused on speech-to-text systems, such as that corpus.
Okay,
Can
thank
I have a
you.
quick comment supporting two answers to the previous questions? Ivan, Evgeny?
Evgeny? your question.
Yeah, can I just provide some more explanation on these questions?
Yes, yes.
Yeah, so okay, so we definitely need to support this work relying on more large size corpora and more rich corpora for different kinds of tasks. Actually, this work was done is very short time period. So the original work was dedicated to the natural language generation based on the link grammar, but at some point we just realized that we can also do natural language segmentation. So first we started to try this on the POC English corpus on the left, and that's kind of gold standard corpus for the framework of natural language processing applications at SingularityNet and OpenCog natural language projects. And when we found that we can solve the problem on that standard corpus, we have started working on larger corpora, such as Gutenberg children. And then we have got the first results, and we just had no physical time to run the evaluation of the other larger corpora, and we definitely need to do that when we proceed further with this research.
Thank you. Thank you for your comment. And I have yet another question about independency from programming language. If I'm not mistaken, then you talked about independency from programming language if we use link grammar, if you use approach based on link grammar. And space is dependent from Python, etc. But I think that if we use link grammar, then we need parser, link grammar parser. And if I use Scala or Haskell or D, then I have to develop this such parser on this programming language. And where I don't understand where is independency from programming language.
Yeah, so we actually do not require the link grammar parser. Our loader architecture operates directly on the link grammar dictionary file, which is independent of the parser. So we built our own custom architecture to automatically load the link grammar rules into memory using solely this dictionary file. So that can be implemented in any programming language. It's not restricted to the same languages as the parser. So we're completely independent of the parser.
Okay, thank you. I don't have any question, but my colleagues maybe have several questions. No? Thank you for your speech.
Thank you.